A very interesting aspect of nuclear power is an entirely different type of nuclear energy generation through the process of nuclear fusion instead of fission. Nuclear fusion, by definition, is the process in which two lighter nuclei react to form heavier nuclei, which are generally more stable. Reactions known till date possess only one final nucleus. Sun and other stars obviously use the process of nuclear fusion to release energy, and fusion is a much more promising process for energy generation than fission. Let's discuss the energetics of a fusion reaction in comparison to a fission reaction. This is a fusion reaction in which deuterium and tritium react to form an alpha particle and a neutron. Fission of uranium-235 releases 200 mega electron volts of energy per uranium-235 atom. Fusion being planned by ITER releases 17.6 mega electron volt per reaction between deuterium and tritium atoms. Now this might seem very small on observation. However, you need to realize that this is between two very light atoms, and this 200 mega electron volt is with uranium 235, which means that the reaction being promised by ITER is much more promisable in terms of energy efficiency. Then an important question is raised. Then why not fusion? Why always use fission? So the main block is that it requires a very high temperature to initiate. It requires temperature in millions of degrees centigrade to initiate fusion. Also, confinement is a major issue. Fusion occurs only in plasma state, where confining the plasma molecules is a real big challenge. Absorption of energy. So basically, absorbing the energy generated from nuclear fusion is not easy at that high temperatures due to thermodynamics. Now, there's a concept of low temperature fusion or cold fusion, which was discussed by two scientists, Martin Fleischmann and Stanley Pons. They declared that they discovered low temperature fusion from electrolysis of water by finding deposits of tritium and large heat in the reaction, and they declared it as nuclear fusion. This is way back in 1970s. Now it is known to be a mistaken result. It was a result which was caused by a mistaken observation. However, cold fusion still remains a topic of interest for a lot of scientists. As we discussed earlier, fusion can occur only in plasma state. So what is plasma state? It is obviously the fourth state of matter: solid, liquid, gas, and plasma. It's a dense mixture of electrical particles. Basically, you can imagine that all the atoms are ripped apart into their electrons and nuclei, which is why they become a dense mixture of electrical particles. At low density, this can be compared to an ideal gas. We can assume that the interactions between them are negligible and try to compare their equation of state with an ideal gas. However, at higher densities, obviously these attraction forces become dominant, and which is why the system becomes too complicated for a simplified mathematical analysis. This is the only state where fusion is possible as of now. Cold fusion is being discussed, obviously. Now I would like you to do this one small example. This is basically a very moderate density plasma calculation. There's an Ni28 plus nucleus on the center. There are 4 electrons on the side of a square. This, forming a circumcircle, has a radius of 10 micrometers. Could you calculate the force experienced by this electron? Worry not, I've done the calculation already for you. If you use some simple geometric methods and simple physics, you will find out that there are some vectors generated, and the net vector of acceleration has a magnitude of this value. This is so huge that it cannot be controlled by any physical means. You have to somehow confine these particles so as to ensure that you do not let this acceleration value be reached. So we require to confine the plasma particles in order to ensure that such high acceleration values are not reached. Confinement is basically trapping them into a space so as to ensure that they are suitable enough for further procedures. Like confinement of plasma is a technique to localize plasma for further procedures, obviously in this case nuclear fusion. Now mechanically plasma cannot be confined. You just now saw the acceleration values. They are so huge that mechanical forces cannot be used to confine plasma. Similarly, it cannot be confined electrically due to the special theorems in physics which state that this is not possible electrically. So the only way to confine them is magnetically. You can only confine plasma using magnetic properties of plasma. And Tokamak and Stellarator are two such confining units which use magnetic forces to confine plasma.
Let's have a look on the design of the tokamak.
A tokamak is the most advanced of current fusion machine designs. In order to get fusion reactions going, you need to keep your fuel hot enough and dense enough, like the center of a star, and you need to keep it like that for long enough for fusion reactions to occur. People have tried and are trying various different ways of doing this. A machine called a tokamak, a Russian design, is the best way we have found so far. The best performing tokamak in the world is JET, which holds the world record for fusion power produced. The word tokamak stands for toroidal chamber magnetic coils. It's a ring donut-shaped vessel with magnetic coils around it that make a trap for the fusion fuel. Inside the tokamak, we heat the fuel to produce a plasma, a superheated gas in the fourth state of matter. We use strong magnetic fields to trap the plasma, and the aim is to hold it stable for long enough for fusion reactions to occur. Within the plasma, the fusion fuels, deuterium and tritium, will then fuse and release enormous amounts of energy. This only happens at high temperatures of hundreds of millions of degrees Celsius. The hot plasma is kept away from the walls of the tokamak by a magnetic field produced primarily by two sets of coils that contain the plasma horizontally and vertically. Fast control systems can change the magnetic field produced by these magnets to keep the plasma trapped and stable.
Let's have a look on the design of the Stellarator.
The Stellarator must have the form of a donut, referred to by physicists as a torus. Particles which find themselves within the cage must follow its magnetic field lines to a first approximation. And if the field lines are bent so as to form closed surfaces in space, then escape becomes impossible, and particles can only repeatedly circle the torus. Shaping of the magnetic surfaces plays a key role in determining the properties of the Stellarator, allowing simultaneous improvement of plasma confinement and stability. Determining the ideal shape is far from simple, however, and only became possible at the end of the 1980s using a computer-aided optimization process. The result of this optimization is Wendelstein 7X, which possesses a five-fold symmetry indicated by different colors for each of the identical sections. Only the outermost magnetic surface is visible at the moment, but there are countless additional surfaces within. If we cut through the torus, we see the puncture points of representative field lines, which form some of these surfaces. It is important to note that each surface is well separated from its neighbors, making the concentric structure of the magnetic cage apparent. Only in this manner is it possible to contain the enormous thermal energy of the plasma for a sufficient length of time. Weighing more than 750 tons, it is a device of imposing dimensions. Measuring more than 15 meters in diameter and reaching a height of 5 meters, fully surrounded by its many-faceted support systems, it is difficult to recognize individual features even from a bird's eye view. To ease the process, individual components belonging to a common system appear in the same color. Let us take a closer look, limiting ourselves for the moment to 1/5 of the torus. Innermost is the vacuum vessel, which in its shape follows that of the magnetic surfaces which it will encompass. The magnetic field is produced by a system of current-carrying coils with complicated shapes which must be maneuvered into place over the vacuum vessel. Although within the vessel temperatures of 100 million degrees will prevail under experimental conditions, the coils, only 30 centimeters outside, must be maintained at a temperature near absolute zero. To be more precise, minus 270 degrees Celsius is required for the coils to remain superconducting, that is, without electrical resistance, so that the magnetic field may be sustained indefinitely. In addition to the main set of non-planar coils, simpler, untwisted coils are also provided to increase the experimental flexibility. We now direct our attention to the region within the vacuum vessel. The metallic luster indicates the divertor and the wall armor, which are the only components which must withstand direct contact with the plasma. Next, we follow the trajectory of a single particle on its flight along a magnetic field line, thereby tracing out the otherwise invisible magnetic surface. For better orientation, the puncture points of several field lines are shown for the characteristic cross-sections we encountered earlier. With a strength of 2.5 Tesla, 100,000 times stronger than the Earth's magnetic field, plasma particles remain closely tied to their field lines and are well confined.
Now, let's discuss about the ITER. The ITER is an ambitious project designed by 7 member nations, including China, EU, India, Japan, Korea, Russia, and US. Yes, you heard it right, ITER even has Indian participation. ITER stands for International Thermonuclear Experimental Reactor. It's a fusion reactor which will work as an experimental reactor for future reactors to come which will work on nuclear fusion. It promises Q equal to 10. We'll discuss what it means. So let's have a look on the objectives of ITER. What does ITER want to achieve? What does it want to do? So ITER firstly wants to achieve a Q value of 10. This is the Joint European Torus. No, it's not a part of the ITER. It's a very old design in fact. It has a Q value of 0.67. So what does Q value actually mean? Q value is the fusion energy obtained per unit input energy given. So this has a value of 0.67. The power given to this was around 24 megawatts and 40 megawatts power was net obtained, which means 16 was fusion power, which is why it has a ratio of 0.67. ITER promises 10, which means they will give 50 megawatt power and they will get 500 megawatt of power back. Next, they are focusing on integration, which is basically connecting the smaller fusion units and trying to guide them and instruct them, and also give a central facility for scientists to study plasma properties. Also, DT plasma sustainability. Basically, the plasma needs to be constantly heated to be kept in a plasma state. So, ITER plans to develop technologies such that this DT plasma can be self-sustained. The heat which is generated during the fusion reaction can itself be used to sustain the deuterium-tritium plasma. Tritium breeding. See, the entire world's supply is not enough for what ITER plans to do with tritium. So the tritium amount required is much smaller than what ITER will require. So tritium breeding is necessary. ITER is thinking over technologies which can be used to breed tritium inside the reactor, making it completely self-sufficient and independent. And also safety demonstration, to demonstrate the safety features, what should be done, giving instructions how to handle nuclear fusion in a safe manner. Let's discuss some other future plans regarding nuclear power. New class of advanced reactors were created in 2019 and they will need to be tested and run. ITER should complete its first test run by 2025. National level production of nuclear fuel will increase by 2022. Also not mentioned here, research is still going on both molten salt reactors and cold fusion. Let's discuss India in nuclear power. So India obviously is building these 7 plants throughout the nation for nuclear fission. India is also planning to open up nuclear power to private firms now. And obviously, needless to mention, India is already a part of ITER. Let's have a look on the career prospects in nuclear power. Nuclear physicists, obviously, because new research always keeps coming. Entrepreneurs, private firms are being allowed nuclear power and now even India is planning to do so. So you entrepreneurs have a good chance. Big data scientists, obviously nuclear power is also having a look on data analytics and try to build new power plants more efficient with respect to the old data available. So data scientists have a good chance. Engineers, obviously, to build and run these plants. Environment scientists, this is something new. So basically the nuclear power industry, people in this industry want to reduce their emission to the environment, carbon or otherwise, which is why environmental scientists have a good chance. Cybersecurity experts. We saw that in India there was a cyber attack. And even earlier, cyber attack has always been a constant threat to nuclear power plants, which is why cybersecurity experts have a very good chance. And finally, politicians, those who might advocate nuclear power and explain its good effects to society and give accordingly the promises. He might stand a good chance to win the election. So let's conclude. In conclusion, I would like to say nuclear power offers a great deal of stability over other power sources. Nuclear waste is much more ineffective and harmless than others. There is still an extensive need for research in nuclear power, especially with terms of cold fusion and molten salt reactors. ITER could be a solution to the present energy